Okay, so just so you have a heads up, the College Board expects you to know the Maclaurin series for e to the x, sine x, cosine x, and 1 over 1 minus x, all of which have been presented to you in one way or another the last two lectures / class meetings. And I'm going to go a little bit further and ask you to also know the Maclaurin series for 1 over 1 plus x squared, which would lead you then to the Maclaurin series for arctangent x. These come up a lot in multiple choice questions and free response questions, and to make sure we're all good at them, this will be part of your next mastery quiz once this exam's done. Okay, so as far as today, we now know how to build a power series for a function. We call them Taylor series, we call them Maclaurin series if they're centered at 0. We know how to do that. We also know that you can create new series by integrating a power series, differentiating a power series, making a substitution into a power series, or multiplying or dividing a power series by something. Okay, so now that you know how to build one, we'd like to know what values of x is it actually good for. In other words, what can I plug into this power series and still get a convergent value? Sometimes that's all real numbers, sometimes you're limited, okay? So I'm going to remind you that there were 3 possibilities for a power series to converge. Number 1, it may only converge at the center, which is not a very exciting power series, but nevertheless it is what it is. It shows you that you have to converge at least at one point. Okay. Number 2, you can converge on an interval that's a subset of the real number line. So for example, -3 to 2. Maybe inclusive, maybe not inclusive at the endpoints. And then the last possibility is your power series might converge for all real numbers. Okay, we're going to start to look at how do we figure this out, where a power series will converge. So the test we're going to teach you today is called the ratio test. First part of the ratio test says take this expression, the absolute value of a sub n plus 1 over a sub n. And remember that a sub n is the expression that is inside the sigma. Okay, so in general we write a series as sigma n starts at either 0 or 1, goes to infinity, and then whatever's inside, that's the a sub n. Okay, the general nth term. All right, this may have x's in it, it may not. Okay, so it says take the nth term and put it underneath the nth plus first term, put absolute value bars around it, and then take this limit. Okay, that's the first part of the ratio test. Now, what are we looking for? If or when this limit is less than 1, the series will converge. So we're going to look at what value comes out of this limit that we take. If it's less than 1, okay, cool, converges. If the limit is more than 1, the series is going to diverge, which leaves us with the last case, if the limit's equal to 1. Okay, and this is a big part of this ratio test, then the test is inconclusive. We're going to need a different test besides the ratio test. Okay, and this will come into effect later on when we start to look at the endpoints of our interval of convergence here. Now, before we get into actually working some of these out, I want to talk about why this actually works. Okay, power series look like constant, okay, a formula of constants times x minus a to the n. Okay, that's what a power series looks like in general. And so this looks almost like a geometric series, right? A geometric series looks like a times something to the n. Okay? The only difference here is that the a is constant in a geometric series, so it's the same. Here, these expressions of n change each time. Okay, so they're not. It's not quite a geometric series, but it behaves somewhat like one. All right, and so the idea here is when you take the nth plus first term divided by the nth term and say that it's less than 1. Okay, if that's the case, then your power series is eventually behaving like a convergent geometric series, where your common ratio is between -1 and 1. Okay, that's the basis for why this ratio test works. All right, let's jump into some examples. All right, first of all, let's just test the ratio test on a series that does not have x in it. Okay, this is just a series of constants. So again, if you wrote this out, this would be 1 over 2 plus 4 over 4 plus 9 over 8 plus, where am I at now? 1, 2, 3, I'm at 4. So 16 over 16, okay? Plus dot, dot, dot. All right, does this series converge or diverge? I don't know. We're going to test it with the ratio test to see what comes out here, okay? So the ratio test says, let's take the limit as n goes to infinity of what? Well, I need the absolute value bars. I need the nth plus first term divided by the nth term, okay? So the nth plus first term is what you get when you would plug in n plus 1 into this expression here. So that's going to be n plus 1 quantity squared over 2 to the n plus 1. That's the nth plus first term. Divide that by the nth term, which is what's given in the expression right now, which is n squared over 2 to the n. Okay, we have to evaluate this limit. Okay, well, first of all, excuse me. First of all, we're going to rewrite this as not a compound fraction. Okay, so we're going to flip the guy and multiply and make this a little bit nicer. And I'm going to say right now that this takes a little bit of getting used to as far as writing all this stuff out. You got to be very careful. It's very easy to get messy and sloppy when you do these limits here. But we're hoping that a lot of these things cancel out. And let's see here. You're going to have 2 to the n in the numerator. In the denominator, we're going to have 2 to the n plus 1 times n squared. Okay? Now, what can we do with this? Well, I have a 2 to the n in the numerator and a 2 to the n plus 1 in the denominator. So, I can do this. A little bit of factoring magic here. 2 to the n. I'll go ahead and multiply out this binomial here, okay? N squared plus 2n plus 1. Now, what do we got here? 2 to the n times 2, right? That's 2 to the n plus 1. And then we still have this times n squared here. All right, now, what can we do here? Well, first of all, I can cancel a 2 to the n and a 2 to the n. And now, I can kind of mentally do L'Hopital's rule here, I think. All right, I have n squared plus 2n plus 1 over n squared. If I was doing that limit off to the side, I would do L'Hopital's rule because right now it's infinity over infinity. So we would go 2n plus 2 over 2n, still infinity over infinity. And then one more time, we would go 2 over 2, okay? So this over that limit is 1. Okay, if you're not sure about that, go do it off to the side. This is why I say you can be sloppy. You can't just assume things, but some of these things you can do mentally. Now what's left? You have a 1 in the numerator, and you have a 2 in the denominator. So our limit's equal to 1/2. What does that mean? Well, 1/2 is less than 1, so this series, sigma n squared over 2 to the n, converges by the ratio test. Okay, now I didn't cover these up, I probably should have, but in the book, this is section 11.6, the directions will say something different. Ignore that for now because we're not at that stage yet, but use the ratio test on these two examples and check them for convergence or divergence. And remember, if the limit comes out to be 1, no conclusion can be made. Less than 1, okay. More than 1, okay. Equal to 1, no conclusion. All right? Come on back when you're ready. Okay, so now let's apply the ratio test to a power series. So now x has entered the game. And I'd like to know, okay, when does this power series converge? And since x is in the ball game, it's probably going to be one of those three scenarios. It's either going to be only at the center. In this case, the center is 0. It's going to be on an interval that's a subset of the real number line, or it's going to be all real numbers. By the way, you should recognize that this is the series for arctangent x. You have to start to recognize the series in their forms written out, and also in their forms with the sigma, with the nth term. Okay, what are we going to do? We're going to do the limit as n goes to infinity of the nth plus first term, and this is in absolute values. Now, here's the deal with the absolute values, guys. The absolute values is going to knock out the flipper, because it's going to make all my terms positive, so I don't have to write the -1 to the n anymore because of the absolute value bars. Okay, so that's kind of a nice little deal here. All right, now watch this. When I plug in, careful here, when I plug in n plus 1 in for n, okay, I have to distribute that 2. So I now have 2n plus 2 plus 1. So that's x to the 2n plus 3, okay, over, you know it, 2n plus 3. Okay, be careful with that. All right, then divided by, big fraction, my nth term, x to the 2n plus 1 over 2n plus 1. Okay, now next line we're going to rewrite this without the compound fraction involved. So I have, and I'm going to go ahead and start separating things out because I know what I'm about to do. Okay, I have x to the 2n, right, times x cubed. All right, what else ends up in the numerator? 2n plus 1 ends up in the numerator, divided by 2n plus 3 times x to the 2n times x to the first. Okay, hopefully that looks good. And now we go ahead and start to look for things to cancel. All right, obviously we have a x to the 2n, we have an x to the 2n. I can cancel one of those with one of those. That's a x squared now. And this is infinity over infinity. L'Hopital's rule makes it 2 over 2. So these two terms cancel out here. Okay, what does that leave me with now? Okay, I'm left with there are no n's left anymore, so I just have the absolute value of x squared. That's what my limit comes out to be. All right, so that's a variable expression. Now what do I know? For the series to converge, that needs to be less than 1. From there, I'm going to say, okay, that means this is going to be less than 1 and greater than -1, and now I've got to figure out what values make that work. Okay. Well, x squared is never going to be negative, so I can ignore that part. But when is x squared less than 1? Okay, in inequality world here, we're going to move this 1 on the other side. Okay, and make a sign chart for this. -1, 1, make that expression 0. And let's see here. Negative in the middle, positive, positive. And we want the ones that are negative, okay? So this series here will converge when x is between -1 and 1. So you can write the answer like this. Okay, now the center of this series is 0, and so I think the book in the back is going to write the answer kind of like this. Let me just show you. So 0 is our center, and I can go out to the right as far as 1, and to the left as far as -1. Okay, so and maybe these work at the endpoints. We don't know yet. We'll find that out later. But this is my area of convergence here. Okay, I've gone 1 unit to the right and 1 unit to the left. Okay, so the term that is used in the book here is radius of convergence. Okay, it's how far away from the center I'm allowed to go. Okay, so in this case, the radius of convergence is 1. I can go 1 unit to the left I can go 1 unit to the right. If you imagine the center is like the center of a circle, okay, and the radius is how far away from that center I can get and still be in the circle. Okay, so that's the term, the radius of convergence. In this case, it's 1. The little interval is -1 to 1. We're going to look at endpoints later because this might converge at endpoints. We need other tests to figure that out, so we won't talk about that just yet. Okay, one from the book that's on a power series sort of like this is 11.8, number 9. Notice 11.8, not 11.6. And this works for both editions. Okay, both editions. All right, let's try another one. Here is the series for e to the x that you're going to start to recognize. Okay, x to the n over n factorial. This is centered at 0. When does this converge? Let's find out. We're going to use the ratio test, which says let's take the limit as n goes to infinity of absolute value n plus first term x to the n plus 1 over n plus 1 factorial all over x to the n over n factorial. Let's get a little bit thinner pen. Okay, first thing I want to do is I want to write this without the compound fraction, and I'm going to start to factor some of these terms so I can see what's going on here. Okay, absolute value, x to the n times x. What else ends up in the numerator? N factorial, right? Flip the guy and multiply. Denominator, okay, n plus 1 factorial. I'm going to write like this: n plus 1 times n factorial. And then what else do I have down here? I have a x to the n. Okay, close my absolute value. Look for things to cancel. Okay, goodbye, 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 goodbye. Now, take the limit as n goes to infinity. That gives me x, which is a variable quantity, over infinity. So this limit equals 0, no matter what x is. What does that mean? Okay, well, isn't 0 is less than 1, so this converges. Now, what does it converge? Always. Okay, converges for all real numbers. So your series for e to the x is a really good one. Okay, there are no restrictions on it. Now, the back of the book, when you get this situation, is going to say that the radius of convergence is infinity. Okay, which makes sense, right? Because you can go either way, both directions, as far as you like. Okay, so the radius of convergence is infinity. That's how the book's going to write it. Okay, but this converges for all real numbers, this series up here. Okay, next entrance ticket problem. 11.8, number 14. And we have one more example to look at. Okay, another power series. So, n factorial times x to the n, when does it converge? It must converge at least at the center, maybe on an open interval, maybe for all real numbers. So, ratio tests will help us determine this. The limit as n goes to infinity of the absolute value, n plus 1 factorial times x to the n plus 1 over n factorial times x to the n. This one does not have any compound fractions, so that's nice. Let's go ahead and start factoring some things here. The limit as n approaches infinity, absolute value, n plus 1 times n factorial, x to the n times x to the first over n factorial x to the n. Close my absolute values. Alright, what can cancel out here? Well, that can cancel with this, and this can cancel with this. And I'm taking the limit as n goes to infinity of n plus 1 times x, which comes out to be infinity. What does that mean? Well, Infinity is greater than 1. So no matter what x is, this series will diverge except at the center. Except at the center, okay? If x is 0, then you have sigma 0, and if you add up zeros, you will converge to 0. Not very exciting, but hey, that's what it is. So converges only at one value, the center, okay? Converges at x equals 0. And the book's going to say that the radius of convergence is 0. Because you can't go any units away from the center to get convergence, okay? So the radius of convergence will be said to be 0. So as far as using this power series for anything useful, not going to happen, right? Because it's only going to converge for one value. So these do pop up, and we got to be able to recognize that they do. Okay, last entrance ticket problem, 11.8, number 23. Please email me 2 questions that you have on the lesson, and we'll see you in class. Bye-bye.